All right, so we're going to do a specific example, okay, of this rational root theorem. Then we're going to, I've already kind of laid the proof out, and I want to walk through the proof with you, okay? So I think it's important to see why P over Q, why factors of 6 and why factors of 2 as a fraction, why do those work if we're going to have zeros, okay? So I'll explain that to you, and then as we're discussing this, my hope is that we realize that ultimately this can be kind of a pain in the butt process. It's our catch-all safety net for factoring anything. Remember, factoring quadratics, what's the safety net for factoring quadratics? Quadratic formula, okay? So this kind of takes the place of the quadratic formula for things of higher degree. 3, 4, 5, okay, those powers. This is kind of the quadratic formula process. And saying that, it becomes kind of a pain in the butt because of the amount of things we have to check. Because the quadratic formula is going to be something that when we use that, I mean, we just plug numbers in, evaluate, and bang, we got our two solutions, right? Here, we have to pick from a list of values that are potential solutions. That picking process can be time-consuming. Okay, there are going to be times where you don't know where to start. Okay, you don't know once you get a result, what does that result tell me about what next number to choose, that kind of thing. So what I want to do is I want to talk about this example and talk about those types of things as we work through this. Okay, so the first thing you're going to do is you're going to find what your p-values are. Okay, p-values are factors of, we'll call that a sub 0 for our generic polynomial. Your p-values are factors of that. Okay, so factors of 6 are going to be plus or minus 1, 2, 3, or 6. Do you guys agree with that? Now, they're all plus or minus. I usually don't like writing plus or minus for all of them. Okay? And the idea is, positive 1 will divide 6, negative 1 will divide 6 evenly, right? It'll give us a, when we say divides, we're talking about with a remainder of 0. So 2 divides 6, negative 2 divides 6, okay? 3 and negative 3, 6 and negative 6, okay? So identify our factors of a sub 0. And then out here, we've got our a sub n, which we're calling those factors q. So again, there it'll be plus or minus, and then 1 and 2. Okay? And here's where it starts to get kind of fuzzy. If a sub n and a sub 0 were relatively prime to one, meaning they were in lowest terms that did not share a factor. Okay? Here they obviously share a factor of 2, right? If they did not share factors, the number of potential p over q's that you would have would be your a sub n number, the factors of a sub n, so q would be that we got 2 factors for q, right? And the number of factors you have for a sub 0, which is your p, so we got 4 of those. If I take the 2 from q and the 4 from p and use the fundamental counting principle, okay, from geometry or 9th grade, 8th grade math, we would get 8 potential zeros. Does that make sense? But they're all plus or minuses, so it doubles it. So we got 16 potential zeros. Well, this is a third degree polynomial, right? Okay, so if this polynomial does factor to have all rational zeros, okay, then 3 of those 16 will work, meaning 13 of them will not work. Does that make sense? And there's a chance that when you're checking trying to find the ones that work and the ones that don't work, you might not find the 3 that work until you found 13 that don't work. Does that make sense? And you're going to find out, well, that 13 that don't work, that was a lot of work it didn't get me anywhere. It allowed me to say what didn't work, but it didn't tell me what did work. Okay? So that's kind of the idea that makes this a little bit less efficient than we like, but we've got some theorems towards the end of the period today that should, and it's not going to make it the most expedient process, but it should allow you to maybe dwindle your list of 13 or 16 down a little bit so that you're not having to check all of them. Okay? So that's kind of where this will lead to towards the end of the period and tomorrow. All right. So once we find our factors of P and Q, we're going to list all our P over Q's. And this is our potential zeros then. Okay? So all you have to do, so do this systematically. Do not just try to haphazardly put these things together. You're going to take the first P value and then divide it by both those Q's. Okay, so it's going to be plus or minus 1 divided by 1. And it'll be plus or minus 1 divided by 2. Does that make sense? That P value as a numerator, each of these Q values as a denominator. Then do the same thing for the next P value. So 2 over Q of 1 and 2 over Q of 2. Okay? Because 2 and 6 had a common factor, that's going to get us some repeats, right? Isn't 1 over 1 the same thing as 2 over 2? So we'll mention that here in a little bit. Then I'm going to take the third P value, which is 3. And I'll put it over 1. And then put it over 2. And then I'll take my last one of 6 and put it over 1. And put it over 2. And the reason that I'm, from the process of putting each P value over each individual Q value then says that each P value is going to be written as a numerator 2 times. Okay, so the P value of 2 is going to be written as a numerator twice with a denominator of 1 and a denominator of 2, which allows us then to say that idea of the fundamental counting principle allows me to say, why did I know I'm going to have 4 times 2 possible zeros? Okay, that's the reason. So I got 1, 2, 3, 4, 5, 6, 7, 8, right? Okay, that was there's 4 of these times 2 of those. Okay, that gives me the 8. Now, some of those are redundant, and this is the idea, is that we don't want to have the redundant ones in here. So plus or minus 1, this is plus or minus a half, plus or minus 2, that's redundant. I already got it in there, so I don't need it again. Plus or minus 3, plus or minus 3 halves, plus or minus 6. That one's redundant as well. That's the 3 that I've already got in there, right? So doing that allows me to take my 16 potential zeros and now break it down to a list where it's only potentially 12. Does that make sense? So that makes it that's one way of making it a little bit easier. Okay? I would still argue that 12 is quite a few that we have to check here. But these are what we call potential zeros. Okay? Now, because my function was odd degree, I don't want to say I'm 100% guaranteed that one of those is going to work, but within this process, one of those is probably going to work. Okay? Now, we could have some irrational zeros at some point, okay, for our polynomial. But as we do these, I don't think we're going to see too many of those. Okay, so that there will be at least one of those P over Qs that divide into this P of X. Okay, and the fact that it's a third-degree polynomial, maybe understanding my end behavior, maybe understanding my turning point, we could have a couple different things happen here. Let's just kind of talk about the different structures. We could have a graph that maybe looks like that. Okay, so there, how many times do I cross the x-axis? Just one time, right? So I could maybe have just one real zero. So maybe one of these things only works. Okay, and then the other two factors would actually be irrational. Okay, or sorry, not irrational, imaginary, complex. A plus BI type thing. Could I have maybe a situation like this, where I have 1, 0, and then I have one that has a multiplicity of 2. Does that make sense? Okay. Could I have something maybe where I've got just 1, 0 again, but maybe it's a root of 3, a multiplicity of 3 there. Does that make sense? Okay. And the last thing I could have, I think, would be that. Those are my potential. Each one of these zeros has a multiplicity of 1. Just kind of understanding the possibilities of what my graph could look like because it's x to the third. That might also allow me, as I'm finding zeros, to kind of start selecting maybe better ones to choose to see what the next zero looks like. Okay? If you're not thinking of that stuff, if you're not thinking about some of the things I'm going to show you at the end of the period, then this process, you kind of do it blindly. Okay? So what you end up doing is you take your leading coefficient. So 2, we had 1, -13, and 6. And here's the idea. These are potential things that are going to give me a remainder of 0. Any one of those up there right now is no better than the other. So how do I know where to start? Does that make sense? Do I start at 1 and then try -1 and then 1/2 and then -1/2 and then 2 and -2 and then 3 and -3? That's up to you. Do you try 6 and then you start 6 and go the other direction? Do you start in the middle at 2 and maybe work to your right one and then work to your left one? Does that make sense? Okay. However you want to do it, it's fine because none of those do you know anything about. You don't know that one of those is any better than the other. So where do you start? That's the question. Okay. I'm going to say, just because I don't want to miss something, I always start at the first one, and I just go systematically. I try +1 first. If it works, great. If it doesn't, then I go to -1. If it works, great. If it doesn't, then I go to 1/2, and then -1/2, and then 2, and then -2. Does that make sense? Okay. Along the way, though, we're going to find some things out that kind of make that process even better. Okay. So I trisymplectic division. I'm looking for a remainder over here. I'm looking for this thing here to be 0, right? I bring my 2 down, multiply, bring my 3 down, multiply, and I can already determine that that doesn't give me a 0, right? So if it doesn't give me a 0, 1 does not work. 1 does not work. And here's what is going to stink for you guys, is that 1 does not work. So then you got to start over here to the side and go -1. Write down all of this again. 2, 1, -13, 6. And try again. Okay? You might start consuming some paper by doing this. Just go back off of what we said. There's going to be 3 zeros, right? There's going to be 3 of them. We've got 12 potentially right now, so we can go through 9 of these lines finding no remainders before one starts working. So we could have what turns out to be maybe 9 iterations of work that doesn't provide us anything, which you might say, well, that was useless work. Does that make sense? Okay. So now I'm going to bring my 2 down. So it gives me -2, -1, 1. I can already see this isn't going to work. Kind of doing a foreshadowing. I don't want to go all the way through. I know when that number is pretty large, when I add it to that number, it's pretty small. I'm not going to get a 0 here, right? So -1 doesn't work. Okay? Now I'm going to cheat a little bit because I can erase here a little bit easier than you guys can. So 1 and -1, those did not work. Now I go to the next one. The next one for me would be 1/2. Okay, so bring my 2 down, multiply by 1/2, gives me 1. Add those together, gives me 2. Multiply those, gives me 1. Gives me -12, and this looks like it's going to work. So now I get my 0, right? Okay. Now here's where we've got to pay attention. Do I know whether that is a single root, double root, or triple root? Do we know? No, we don't. So we could have, guys, so this point right here, now it would be moved to the right, but that could be a double root, right? That double root could be 1/2. There's nothing up there that tells me whether it is or isn't. I have to try this again. So once I get a 0 with a particular C value, you have to try that C value again. Okay? So I'm going to go, I don't like to rewrite everything. I think it's time consuming. So I'm just going to put another box out here and put 1/2. And I'll just start working here, bring my 2 down, multiply, and I can already see it's not going to work, right? Okay? So 1/2 has a multiplicity of 1. So if 1/2 is the 0, what is the factor that it came from? That's my C value, right? If C is a 0, and we had the theorem last week, if C is a 0 of P of X, then X minus C is a factor of P of X, right? That was the theorem from last week. So 1/2 works. So X minus 1/2, that's a factor. Is that okay with everybody? We're good? Those of us who are not taking notes, we're going to be all right with that? Positive? Okay, this process gets pretty stringent here in a little bit. Okay, so X minus 1. So now, here's the thing. I can keep going. Now, I know 1/2 is not going to work again. We did that. Okay? So I could try negative 1/2. I could try 2, negative 2, and keep going. But be thoughtful. Think about don't be a robot. Think about what you're doing. This was 2x to the third, right? When I divided by x minus 1/2, what does this exponent right here become? X squared. Okay? Do you have a better way of finding the factors of 2x squared plus 2x minus 12 than using that list of P over Q's? Yes. Once you use P over Q enough to where your quotient line is quadratic, okay, that's what we got right here, right? 2x squared plus 2x minus 12 is quadratic. Don't use P over Q anymore because you're going to waste your time, okay? Now, I did try it one more time with 1/2 because I was thinking, well, if 1/2 works, then my final quotient line will be linear, and I'll automatically have this thing factored easily, okay? That being said, now I've got P of X is equal to that factor, x minus 1/2, now times that thing. So I'll write it as 2x squared plus 2x minus 12. You should always be able to take your P of X's and rewrite them as a product of linear factors and or quadratic factors. Okay? And then what's nice about the quadratic factors is because we know we have the quadratic formula, we should always be able to write the quadratic factors as a product of linear factors. So those two ideas together basically say every P of X that you come across can be written as a product of linear factors, a product of these things, where the exponent is a 1. Okay? So how do I address that? What do you think would be the best thing to do there? I want to factor that. Can I take a GCF out of 2? Can I let that 2 just disappear? Why not? Huh? You said because it's important? But why is it important? Okay, I agree, but why? How come sometimes we let it go away, sometimes we don't let it go away? Why would I have 2x squared plus 2x minus 12, and I ask you to factor that? Why do I keep the 2 and write it as x squared plus x minus 6. And how come when I make it an equation, then I just write x squared plus x minus 6 equals 0? I don't care about the 2. Huh? So when I want to factor it, okay, so at the initial, also when I'm factoring, I'm finding the expressions that multiply together to give me that, right? Okay, when I'm solving it to equal 0, I've got two numbers on the left-hand side equal to 0, so I can divide both sides by one of those numbers, right? 0 divided by 2 is what? 0. So as long as I do the same thing on the left-hand side as I do the right-hand side, I'm okay. So that's why when it's an equal, because I get this question all the time. How come sometimes when you factor that GCF out, it disappears, and other times it doesn't? Well, times that it disappears is because it's in an equation. And then we'll divide both sides by that GCF. Okay? Think about this. If I ask you to take the number 24. Let's factor that. That's 2. Now do the prime factorization. So it goes 2 times 12, right? And then 12 is 2 times 2 times 3, right? So the prime factorization of 24 is 2 cubed times 3. Would you ever write that? Would you ever just say, oh, I'm going to let one of those 2's disappear and write my prime factorization of 24 that way? No, because that's not 24 anymore, right? So over here, if you were to just let this 2 go away, well, that's not 2x squared plus 2x minus 12 anymore. Does that make sense, everybody? Yeah, I think that's very important as we're doing this. So that 2 is a GCF that comes out. Does this factor now nicely? As what? X plus 3, x minus 2. And I got x minus 1/2. And now I've got this 2 out front, right? Now here's the nice thing. That 2, guys, is a vertical stretch, correct? Does that make sense? And right there, it's pretty obvious that's a vertical stretch because it's out in front of everything. Okay? If I wanted to graph it, x plus 3 tells me I have a 0 where? Where? Negative 3. Okay, x minus 2 tells me I have a 0 at positive 2. And x minus 1/2, 1/2, right? End behavior looks like this, correct? We'll come up. I know these are first degree zeros or a multiplicity of 1, so I know I'm going to pass through them kind of in a, if I were to zoom in, zoom in just on that 0 in a very, very tight window, it'll be kind of linear as I pass through the bottom half plane to the top half plane. And then my end behavior. So I don't necessarily know what's going on here. We talked about the calculus needed to find those max and mins. I do know that y-intercept is my constant term of my polynomial, which was 6. Don't know how low that goes, but then I do know I model that end behavior. So that gives me the ability, guys, to construct that cubic through the use of factoring. Is that all right? There's no other way of factoring that thing using like special techniques like AC method, grouping, or anything like that. Now here's the thing. That process will factor anything that has rational zeros for it. Okay? My hope is, though, that you realize that sometimes that is a longer way or longer tool than necessary. Remember, if I have this, if you had this here, would the quadratic formula give you the answer to that? If I asked you to factor x squared plus x minus 6, will the quadratic formula work for that? Yeah, but is the product sum technique quicker? Okay, so that argument is still consistent here. Even though we started here with this, and I shot right into the P over Q, you might want to think, is there a factor by grouping here that might actually allow this to be done quicker? There's not. It doesn't work here. You have to use P over Q here. But that's the thing as you go working on in other classes. You don't want to be consuming 15, 20 minutes on a problem that should have, by the structure of it, taken you maybe 30 seconds. Does that make sense? Okay. So always think kind of that hierarchy of factoring techniques. GCF, factor by grouping, quadratic formula. Rational root theorem is the last thing you want to check because it's the longest, most time-consuming. Okay. Is that okay, David? Can we do that? You guys remember doing a little bit of that last year? Okay. The one thing that we got to pay attention to is if we need placeholders. Okay, that throws all my synthetic division off. Okay. Remember to check multiplicities. Okay, if 1/2 works once, there's nothing there that says it's not going to work again, so try it again. Okay. I want to talk about why this works. On Friday, I guess Thursday, we mentioned a little bit. Okay, but this isn't a good enough proof because this only shows us doing this with that particular set of zeros. Okay, but we talked about how, if I FOIL that P of X out there and I get that 24 as my last term, then that means working backwards from the 24, the x cubed minus x squared minus 14x plus 24 line. Working backwards then, the zeros had to be factors of 24, right? Okay, and then we kind of talked about, well, what happens if that number out front here is not a 1, maybe it's a 2 or a 3 or something like that, then what happens? Okay, so we kind of discussed that with what we call the rational root or rational zeros theorem. Okay, I want to prove this with you. I think, now this isn't something, guys, I'm going to recall or ask you to recall right now. It's not something I even want you to write down right now. I just want your full undivided attention to this process. Because when you get to a college class, the specific questions that we were doing, 2x cubed plus x squared minus 6x plus 6, or whatever that last question was, minus 13x plus 6. You don't do a whole lot of that. Okay? You do more of this, because if I could do this, I've effectively factored every single polynomial I could ever come across. Does that make sense? If you can do the proof and understand the proof, that is showing that process works for every single specific case with real numbers. Okay? So here's the idea. This blue statement says if f of x is your generic polynomial. Okay? It says prove that every rational zero of P of x is of the form P over Q, where P is a factor of A sub 0 and Q is a factor of A sub n. Okay? So we're showing why do we choose A sub 0 and its factors? Why do we choose A sub n and then its factors and divide them? Why does that always work to provide the zeros of the polynomial? And here's the logic behind it. Okay? So, it says if P over Q is a zero of my polynomial. Okay, so this again is just that generic polynomial we've talked about, right? Okay. Should have an A sub 0 right there. Okay. If that's the case, then would you guys agree that when if P over Q is a 0, that means the y value turns into be 0 when that's the x value, right? Does that make sense? Okay. Doesn't this make sense then? If I take my function and wherever I see an x, I put P over Q, okay, I should get a 0 back for the y value, right? That's the definition of a 0. That makes sense to everybody? Okay? So what does this mean? Well, this means my function evaluated at P over Q. Well, here's my function, equal to 0. So here's my function. I set it equal to 0, and then I evaluate it at P over Q. That means everywhere I see an x in my function, just replace it with the input value of P over Q. That make sense? Everybody on page here. So what I'm doing right now, let's go back to that specific case. Okay, we had 2x cubed plus x squared minus 13x plus 6. That was, in this case, let's just say that's our f of x. Okay? Well, if P over Q, which would have been, for us, we tried 1/2 first, right? That's what I'm doing, and setting that equal to 0. That's what we're doing right here. Okay? This is the 1/2. When I plug it into here, into my function f, I should get a 0 back. Does that make sense? Okay. Now I want to do some algebra here. What do I get? How do I do something like this real quick? If I had a to the m over b to the n raised to, let's just say, the w, how do you rewrite that using your law of exponents from last year? Think about it this way. Doesn't this mean a to the m over b to the n times a to the m over b to the n times a to the m times b to the n, and this would happen w times? Isn't that what that means? Okay. Well, if that was the case, how do you multiply those two together? You'd have a times a. What do you do with my exponents? Right? When I multiply like bases, you add the exponents, don't you? Does that make sense? So wouldn't you have a to the m plus m plus m plus m w times? Well, how do I say m plus m w times? A to the m w, right? And then don't I do the same thing for the bottom? B to the n w. So you guys remember that when you just multiply those powers? Does that make sense? Okay, so that's the proof of that. That's why that works. Okay, so over here, when I'm putting in p over q to the n, okay, that's going to turn into that right there. A sub n, my leading coefficient, p to the n, q to the n. Okay. Here, take that n minus 1, raise it, or multiply that power of 1 by it, gives me p to the n minus 1, and do the same thing with q to the n minus 1. And just keep doing that all the way through. Okay. Now, I'm going to look at that leading term, and I see that leading term has a q over n in the denominator. And I know that if I multiply everything by q over n, that will go away. And it might not make sense right away why that's going to go away, or why we need to do that. But let's multiply everything by q over n. And we'll take that, multiply by q over n. Take that, multiply by q over n, or q to the n. Multiply that by q to the n, multiply that by q to the n. Okay? I think this one's kind of easy. If I multiply that by q to the n, cancel, cancel, right? Leaves me that. This one's a little bit more difficult. Okay? So let's kind of drag that one to the side here real quick. We've got a to the n minus 1 times p to the n minus 1 over q to the n minus 1. And we're going to multiply that by q to the n, right? Well, that turns into, if I multiply those out, p to the n minus 1, q to the n, over q to the n minus 1. Okay? Are we okay with that? Well, let's think about what that means. That means, if I had, like, let's just do something here to the side real quick. If I had 1 over, like, 3 to the third, can I rewrite that as 3 to the negative third? Is that the same thing? You guys remember that? If I want to flip-flop these, denominators and numerators, I just got to take a denominator to the numerator. I just change the sign of my exponent. Let's do that here. Let's take that up there. And when we do that, some nice things are going to happen. P to the n minus 1, q to the n. Now, I need to negate this. So it's going to be q to the negative n minus 1, right? Well, let's think about that. P to the n minus 1, q to the n times, now it's going to be q to the negative n plus 1, right? Are these like bases? What do you do with the exponents of like bases? You add them. It gives me n plus negative n plus 1. You see what's happening here? What's going to happen with those n's? Cancel. Let's use q to the 1, right? Is that a nice factor? Is that a lot nicer than what it started with? Okay? So when we multiply this thing here by q, multiply that thing by q to the n, it turns into this thing here, which is really nice. Multiply by q over n over here gives me this. Multiply by q over n there. So really, the idea of multiplying everything by q over n got rid of all my fractions, right? That was what I was looking for. Okay? Those things equal to 0. All right, now here's a step that might not make a whole lot of sense right away. Like multiplying by q over n. So I said that at the same time when I said multiplying by q over n isn't going to make a lot of sense right away. But when we're done, we got rid of fractions, right? That's why it made sense to do that. Here, I'm going to subtract that from both sides. I think I put a box there. I'm going to subtract a sub 0 q to the n from both sides. And we get something like this. Okay? So this is just, understand what we've got here, guys. We've got our polynomial evaluated at some value, some p over q. So the idea here is maybe when I evaluated here, maybe when we did this, so far, all I've done is shown that, well, 2 1/2 cubed plus 1/2 squared minus 13 to the 1/2 is equal to now, remember I subtracted the constant over, so it's equal to -6. Does that make sense, everybody? That's all we've done so far in this proof, okay, with the generic information, okay? If I look at this left-hand side, would you agree that each one of those terms has a p in it? There's a p, there's a p, there's a p. Okay, now think about this. If I factor out a p, okay, so let's say that I had like 2p cubed plus 2p squared. If I factor out let's make it 3p squared. If I factor out a p, that's going to be 2p to the what? Second. Is that one less than what I started with? So down here, when I had p to the n, and I factor out p, doesn't what is left over be one less as an exponent? Does that make sense? That's where I get p to the n minus 1. This here, okay, is squared. So I factor out a p there, so it's going to be 3p to the first. Isn't that right there 2 less than what I started with as a cube? That's where I get the n minus 2. Okay. Now here's what, so all this algebra, guys, and that's all that is, a little bit of algebra 2, okay, is getting this thing so we can make a comparison, so we can make an argument. And here's the argument. Would you agree that the left-hand side is equivalent to the right-hand side because it's an equation? That make sense? That's all equations are, is they tell you the left-hand side is exactly the same as the right-hand side. Would you agree that this is just a number? Let's put number subscript 1 times, in parentheses here, a second number. Does that make sense? Okay. Obviously, when I know what these p's and q's and coefficients are. And then over here, I've got another number called 3. This a sub 0 is number 3. And that would be number 4, q to the n, right? Does that make sense? So the left-hand side gives you a product of two things. The right-hand side is a product of two things, right? They got to be the same. Those products have to be the same. It's an equation. So here's what we're saying then, okay? If we go back up to what we argued at the beginning, P over Q was in lowest terms. What that means is that Q will no longer divide P evenly, right? That means like P might be 2 and Q might be 3. P might be 5 and Q might be 7. It does not say 3 and 6 because those are not in lowest terms, right? Make sense? So because P and Q are in lowest terms, we say they're relatively prime to one another. They don't share a factor. P and Q do not share a factor. Why is that important here? Because if I divide this entire left-hand side by P, what would I have to do to the right-hand side? If I divided that entire side by P, what do I have to do to the right-hand side? Divided by P. And here's the argument. Because P and Q at the beginning were in lowest terms. Will P and Q divide evenly here? Will P and Q divide here? If they were in lowest terms to begin with? No. But if this side here was identical to this side, that P needs to divide into this somewhere. So if it doesn't divide into the P or into the Q to the N, what does it have to divide into? Does it have to divide into A sub 0? Does that make sense? So does that show you that P is a factor of A sub 0? P is a factor of my constant term. Okay? The argument kind of show you this with specifics. So here's my P. Here's the garbage that was in the parentheses. Don't care what that is. Okay? Let's say our P was a specific value of 2. Let's say our Q was a specific value of 3. Okay? Those are in lowest terms to one another, right? Okay? They're relatively prime. If I were to expand this right-hand side, that means times 3 times 3 times 3 n times, right? Well, will 2 divide that? Will 2 go into any of those? Will 2 divide 3 here? Will divide that 3? Will divide that 3? No, right? So that P does not divide my Q to the N, but if these are equal sides, it must divide that then. Okay, and that's the argument that we're coming up with, is that this proves that if P over Q is a 0 of F, then P is a factor of your constant term. The rest of this goes back to the beginning when we multiplied everything by Q to the N. And now instead of subtracting the constant term across, I'm going to subtract that term to the other side. Okay, and it gives me this line here. And now in that line, everything has a Q in it. Does that make sense? So I factor a Q out. And now I've got the left-hand side equal to the right-hand side. Well, if P and Q were in lowest terms, that's not going to divide. They're not going to divide each other evenly. So if that doesn't work, Q must only divide A sub n, which was your leading term of your polynomial. Does that make sense? Okay. So, what I want you guys to understand is that is the algebra. What we're doing here is using that information to do a specific case. Does that make sense? But the reason we can do it all the time now is that proof. And that's what I want you guys to open your eyes to. Am I saying you're going to have to be able to do that? No, because I think that's a very difficult thing right now as a high school student. Okay, but what I wish I would have known taking a mathematics kind of route in college, okay, is that was waiting for me. Okay, not to scare me, but to prepare me to understand as a high school student. If I would have known how to use the rational root theorem with specifics and what it was doing for me and all the kind of intricacies and caveats of it, and to learn that well in high school, then I wouldn't have had the struggles in college that I had when I came to actually being told on a test, prove the rational root theorem. Does that kind of make sense? Okay? So I want you to open your eyes at it, because now, if we take the approach, I'm going to learn how to do these specifics, these ones with provided coefficients, and I can do the work, not be a robot, but understand what I'm doing and why I'm doing it. And later on, the math classes that you might experience, the science classes you might experience, are going to be so much easier for you. Okay? I've assigned a 3.4. Okay, it's going to be due Thursday. We'll get through this stuff. I want to do a couple more examples tomorrow, but there's two theorems that are going to help us kind of dwindle that list. That we first had 16 possible zeros, then we saw redundancies, so we got that down to 12. But at that point, we had to check 12 of them. We've got two theorems, Descartes' rule of sign, and the upper and lower bound theorems, which should allow us to dwindle those lists a little bit more. Okay, to where maybe after trying one of those zeros, maybe I can cut my list in half then from 12 to 6. And those are nice things to use in conjunction with the rational root theorem. we'll do that tomorrow. Spend a little bit of time on Wednesday on that. And then Thursday, that's the time that we do. Okay? Looks like we're going to have some wasted snow today. See you tomorrow, on time. They're letting us out today early. Mr. Shine said 275. Oh, I thought you saw a mirror.